All right, here's a video for reviewing Gauss's law. Ultimately, we're going to be using it to determine the electric field for symmetrical charge distributions. In AP Physics C, we only need to concern ourselves with symmetry with our most common types of problems. And what we ultimately need to concern ourselves with is how much charge is inside. That's the main crux of our problems. Before we get started, we need to make sure we're thinking a little bit about electric flux and what that is. It's the amount of electric field that's going through a surface, and we want it to be, I like to think of it as being perpendicular to the surface, although I have seen it referred to as parallel to the normal of the surface, but I like to think of it as going perpendicularly through the surface. You would have a maximum amount of electric flux that way, whereas if you if they were parallel to one another, you would have zero. There's a cosine or sine, depending on how you want to look at it, associated with this statement, but I'm just focusing on the maximum because for our charge distributions and the way we're solving them with symmetry, we're only going to need to concern ourselves with the electric field times the area in which the electric field is passing through. So that's the electric flux phi. Putting some of these ideas together, we're going to realize that our Gauss's law statement is that the electric flux is equal to the Q enclosed over epsilon naught, where Q enclosed is the amount of charge inside of a Gaussian surface. And we make a substitution translation with electric flux to say that that is EA, and that's Q enclosed over epsilon naught. And then finally, the ultimate goal is that we will be finding the electric field, and we can do that by finding the Q enclosed over epsilon naught A, or A epsilon naught, where A is the surface area of our Gaussian surface, and Q is the amount of charge enclosed inside of our Gaussian surface. Some symbols that you'll see me using potentially are lambda, sigma, and rho, where lambda is for a linear charge distribution, typically associated with a wire. Sigma is a surface charge density, whether that's a hollow sphere, a plane, or the surface of a wire, or like a straw-like device. And then finally, rho, the volumetric charge density, that's used for solid, non-conducting objects where you have the amount of charge per unit volume. Sometimes these are given to you either in this form, and you can translate them to this form. The types of problems that we need to be aware of and comfortable with working on are, for using Gauss's law, is spheres, cylinders or wires, and planes. And associated with those are the Gaussian surfaces that I use in my class. You can also use some rectangular prisms if you want. However, these are what I will be using for the rest of this presentation. So we'll get started here. Gauss's law with spheres, just some things to think about. We need to think about the surface area of a sphere is 4 pi r squared, and the volume of a sphere is 4/3 pi r cubed. So here's our first problem. We have a sphere, and the sphere is either hollow or it's conducting, meaning all of the charge resides on the outside. One thing that you would want to make sure that you're aware of is if you have a conductor, the charge will move to the outside of the surface so that there is no charge inside. It's only on the surface of the object. So a type of problem could be, what is the electric field located at the 2 points? So I have A and I have B. Since it's a hollow sphere, it's conducting. We've talked about the radius of the sphere. We can identify that as being R here. And then at some point B, which is not R, it's beyond the scope of our sphere. So when we're looking at this, we want to think about where is the charge and how much is inside of this Gaussian surface that we're drawing. So what we would want to be aware of is all of the charge for this problem is located here on the outside. Now this is a two-dimensional representation of a sphere, so it's just a circle, but imagine it's 3 dimensions. And we would say that all of the Q is located here. What would we be aware of is we could start drawing some electric field lines, and those electric field lines would be radiating outward. I've indicated that it's a positive Q, so we'd have electric field lines radiating outward. A question that you may begin to ask is, what about the charges that are also pointing away from the surface, but in the case of this, inward into the center of the circle? For every right arrow, everything like this charge right here that has an electric field that would be pointing to the right, to its right, because electric field lines point away from positives and towards negatives, would have significant counteraction with charges that are against it on the right side of the sphere with their electric field lines pointing to the left. So everywhere inside the center of this sphere, either whether it being hollow or conducting, the electric field cancels out to always be 0. Inside a conductor or an empty space, the electric field will be 0. So we can go over here and we can immediately say that at location A, the electric field is equal to 0. The electric field at A is equal to 0 everywhere inside. How about location B? Well, what we want to do for location B is we need to figure out Q enclosed. So I'm going back to the electric field is equal to Q enclosed over A epsilon naught. My apologies. So how much Q is inside of this whatever's at B? So we need to draw a Gaussian surface. A Gaussian surface must be symmetrical, and it must enclose all of the charge. And ideally, we want that Gaussian surface so that the electric field lines are passing through perpendicular to its surface. The way we can draw something that's perpendicular to this is we could draw a sphere around that other sphere, and that is so ugly, but it's what we got for right now. What we would see is that these electric field lines that we initially drew would be permeating through and would cross through point B, and all of them would hit that surface perpendicular to it. That would maximize our amount of electric flux, where our electric flux is E times A, and then we would be able to now determine the Q enclosed. We can do the Q enclosed lots of different ways. I've described that the Q is distributed evenly about its surface. So we can either find a surface charge density, or we can say that the amount of Q inside of this surface is all of this Q. Okay, so we can say that all of this Q is inside, and we would then be able to identify that this turns into a relatively simple problem. Hollow spheres, you don't necessarily need to use Gauss's law. We're going to see that the Q enclosed is Q, and our surface area for our Gaussian surface is some value, and we need to call this, we'll call this lowercase r. I define that the radius of our original sphere is capital R. So we keep going, and we will then need to define the surface area of our Gaussian surface. I'll go over here, surface area of our Gaussian surface. Well, that's going to be 4 pi lowercase r squared. And we then plug in what we know. We know that the amount of Q enclosed is capital Q. We divide that by 4 pi r squared epsilon naught. And if you remember this from previous ideas, 1 over 4 pi epsilon naught, it happens to be Coulomb's constant K. And so anytime you're outside a conducting sphere or a hollow sphere, you can say that the electric field is simply equal to KQ over R squared, or how you would have defined it in electrostatics for a point charge. Anywhere outside a conducting sphere or hollow sphere, you can define the electric field for a point charge, KQ over R squared, where your R must be from the center of your original sphere. You're more or less treating it like a point charge at this location that I've indicated here as letter A. It gets a little bit more challenging when you start looking at non-conducting spheres, where I have now a sphere with a radius r and a charge q evenly distributed throughout its volume. I used a pencil here to shade to indicate that this is a solid non-conducting sphere. And I want to know what the electric field here is at point A and at point B. Wait, I want to go do one thing right here. I find this to be a nice tool to use while you're thinking about this. So when you have this type of problem, if we were to graph the electric field as a function of position, so we'll put this as a value of R, and we'll put electric field on our vertical axis. What I will indicate to you here is where that capital R is. Capital R would be the radius of our original sphere, and what we would identify is the electric field inside all the way up to there is 0. Anywhere inside a conductor and anywhere inside of a hollow sphere, there is no charge enclosed. It's all on the surface. Therefore, there is no electric field inside because Q enclosed is 0. What happens is that then it jumps up like a discontinuity, and then it decays proportional to 1 over R squared, where this is KQ over R squared now. So it jumps up and then decays. So we must keep that in mind. For non-conducting spheres, we'll also draw the graph. I apologize for not doing that already. I forgot. I meant to do it, but for non-conducting spheres, we need to think about a few things. And what I want to do first is I want to identify something. I need to define a term. I'm going to define a term with what we have here. Because this Q is evenly distributed out throughout, I have little Q's here, here, all evenly distributed. There's types of problems that are a little bit more challenged where you integrate, but we want to make sure our first approach here in review is just for straightforward cases. So we would have Q evenly distributed throughout its volume, and we have a radius R, and we want to then define the volumetric charge density. I want to define what this rho is, the amount of Q per unit volume. We know that this is a sphere, so I'm going to put the Q enclosed. That's what that is, and I need to take it per unit, or Q per unit volume. So that's the Q that's evenly distributed throughout its volume, and then V the volume. So no matter how much volume I take, I will always have the exact amount of Q that I'm looking for. Then what I want to do is I want to take Q and I want to divide it by the volume of this sphere. Well, what's the volume of this sphere? It is 4/3 pi R cubed. Sorry about that. So we got Q per unit volume, and this is a constant now. So now what I need to do is I just need to multiply this by how much volume I concern myself with, and then I would know the amount of Q enclosed. If you want to think about it, rho V, shifting this around, would be equivalent to Q. So however big my Gaussian surface is would dictate this volume, but this rho is always going to be associated with this. The maximum my Gaussian surface volume for this to be useful is the maximum volume of this sphere. So once I get here, the problem changes. So let's do A, which is inside the sphere. I also have B, which is outside the sphere. So we're going to look at A first, and we need to define some value R that is located at. So how about we just call it RA, the radius at location A. Okay, I need to then start with Gauss's law. I just think of it now as E equals Q enclosed over epsilon naught A. So epsilon naught's constant. We need to draw our Gaussian surface. Because this is a sphere, we draw another sphere at that, and we can now define a few things about that sphere. We know the surface area of that sphere is 4 pi RA squared, and we know that the volume of that Gaussian surface is 4/3 pi RA cubed. So the surface area of our Gaussian surface is 4 pi RA squared, and the volume of our Gaussian surface is 4/3 pi RA cubed. why is it important to have 4/3 pi RA cubed as this volume of the Gaussian surface that we didn't worry about before, is because I need to worry about how much charge is located here. Inside of this Gaussian surface, what's my Q enclosed? That's the crux. We need to know what the Q enclosed is. Well, I know the amount of Q per unit volume. I've defined it as rho. So I go over here and I would just say, what volume do I concern myself with? I concern myself now with the volume of my Gaussian surface. So when I want to find Q enclosed, the substitution looks like this. The rho that I got over here for defining the amount of charge per unit volume for this non-conducting sphere times the volume of my Gaussian surface. When I multiply those two values, I would get the Q enclosed. I wouldn't have all of it, but I'd have some of it, and that's the amount that I would have. Divide that by epsilon naught times 4 pi RA squared. Constant, R squared, epsilon naught. So we have here a number, right? That's now a constant value. You know that when you're using any type of integration or derivative, constants make problems very easy, or easier. I don't know. Is it easy? Are there such things as easy integrations? So this makes the problem more accessible. But then we think about what's up here. So then I have my rho, which is a constant defined earlier in the question. My volume being 4/3 pi RA cubed over 4 pi RA squared epsilon naught. When I look at this, I start seeing some things canceling out. I see this 4 canceling out with that 4. I see the pi canceling out with that pi. I see this RA squared, 2 of those canceling out with 2 of those, leaving me with only one RA in the top. And then I can write for this statement, after working it all out, rho RA divided by 3 epsilon naught. And that will tell me the amount of electric field located at A. To do this problem, ensure that you define the volumetric charge density by taking the amount of charge and dividing it by the total volume of the object. To find the Q enclosed, you take the total volumetric charge density and you multiply it by the volume of your Gaussian surface. This value is proportional. Look at this. This is a constant, and we would say that the electric field is now proportional to, while inside of our Gaussian surface, using this electric field per unit distance, R. We would say all the way up until we get to the surface. We called that capital R. We would increase linearly until we reach its surface. Once we reach its surface, we no longer need to concern ourselves with finding out the Q enclosed by using this rho Gauss times the volume of the Gaussian surface, because once our Gaussian surface is as large as this, we can no longer get any more Q enclosed. That's where it stops. That's where now anywhere outside, we would only have Q. So by the time I get to location B, we are outside a sphere, which we can now treat as a point charge with a charge of Q. So we've got, for location B, we have another simpler problem. The electric field is then equal to KQ over RB squared. That is very similar to what we had defined here. Electric field is KQ over R squared. When you're outside a sphere, that works out. So then we have this, and we begin to decay, and our decay is proportional to 1 over R squared. Here, it's proportional to R. It increases, and then it decreases inverse square relationship. Next, we have a wire. Problems get a little bit different. I'll work through this one a little bit more thoroughly. We want to say that here we have a positive charge residing on this wire, and I want to find the electric field located here at location A. So I'm going to put this is all plus. Okay, there's a bunch of pluses here. Well, what direction do electric field lines point around positive charges? They point away from positive charges. So it points radially away. So we have these electric field lines that are pointing away up top. Down below, they're pointing down. And then you also have some of these electric field lines that are pointing out at you and down away from you, all the way around. Okay, so like spokes of a wheel. So we have all of those. And what we need to do is when we draw our Gaussian surface now, we need to make sure that our Gaussian surface makes all of these electric field lines travel perpendicularly through it. So we pick a Gaussian surface, and the shape that we'll use is the part of a cylinder that would be the outside of this can. So if I put the can like this, and if I were to slide it through, you would see that those electric field lines would be piercing this can, and everywhere that they pierce the can, they would strike the surface perpendicular, as long as I put the wire at the center of the can. We're not concerning ourselves with the top and the bottom, just this rectangular plane. So I draw it. It doesn't matter how long you draw it. We're going to see some things canceling out. So I've got this. I drew a line. Let me draw it in a different color. You have a line here. Drawing my can. A line there. And then we would be able to see this side of the can. And everywhere we have these electric field lines will be pointing perpendicular from it. We then begin our problem by identifying that the electric field is equal to Q enclosed over epsilon naught A. Always important to start a Gauss's law problem with this information. Because we have epsilon naught A and Q enclosed, I need to find how much Q is enclosed inside of this. So then I need to define what, in this case, I said with a wire on the conducting wire. So it's a conducting wire. The radius of the conducting wire is R. So I'm going to do a sigma, or a charge distribution, that is along the surface of this. So that means I need to take the Q divided by the surface area of my wire. Well, what's the surface area of it? Oh my gosh, what's the surface area of this? Well, we know it's the area, so it's 2 dimensions. It happens to be 2 pi r. That's the circumference of the wire, but we need to take another value into account, the length of the wire. So we have 2 pi r L, and that would tell us the amount of charge per unit surface area. Notice that our surface area has a length component in it, so keep that in mind. And then I go over here, and then I need to define the surface area. This is the sigma, and then I need to define over here the surface area of my Gaussian surface. So the surface area of my Gaussian surface would be equal to 2 pi r A, this should be capital R, RA times some length L. This length L and this length L need to be the same. So then I need to go into here, and then I need to figure out how to solve this problem. Very similar to what we did before, to find the Q enclosed, how much charge is inside of this. To get Q enclosed, I need to take my sigma, and I need to multiply it by an area. Then I need to divide that by epsilon naught times the surface area of my Gaussian surface. What we will find here is sigma constant times the area. In this case, it's going to be all of it. So I'm going to multiply that by 2 pi capital R L. You see that that actually ends up being just the Q, which is what's important. We're outside, important to note, divided by epsilon naught times the surface area, 2 pi R A L. If you wanted to think about it, we can see that these two L's would cancel out. And the only thing that would matter is how far away we are from the surface, or from the center in this case of this wire, to location A. We've got a constant, cancels, 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 cancels. Defined, and there you go. Finally, planes and parallel plates, ultimately defining a uniform electric field. We're going to start by talking about the top plate. And at the top plate, again, we have electric field lines that are pointing like this. But what is different in this case is these electric field lines don't point radially around it. They just point perpendicular to its surface. So in the case of our can, we no longer look at the can this direction. We look at the can in this orientation, actually, in this orientation for this problem. So I'm still using a Gaussian surface that's a cylinder. But the way I want to think about it is like this. Like a straw piercing the conducting plate. So when I do this, I need to define how much Q is inside of this, and then I need to be able to describe the distance that this is away. Now, there's two sides of this, so we need to keep that in mind, that there's two surface areas that this electric field will be piercing. So there's a couple slightly different ideas that we need to think about. But ultimately, we see a very elegant statement at the end. So for the top plate, we're defining the electric field, and that is equal to Q enclosed over epsilon naught A. Where Q enclosed is going to be dependent upon this surface charge density that I already gave you, the amount of charge per unit area. So in order to figure out that Q enclosed, I need to take this Q, the sigma, and I need to multiply it by the area. Well, what's the area that we've enclosed it by? We've enclosed it by the circumference, or the surface area, excuse me, pi r squared of this Gaussian surface, the top and the bottom circles of our cylinder. That's the Q enclosed. So I'm going to define that as pi r squared. And that's what we have going on here. Okay. Then I have here, I have epsilon naught, and we have two surfaces now. We have it going through the bottom and we have it going through the top, but they're both hitting it perpendicularly. So we still get maximum flux, but we need to take into account both the top and the bottom. So I need to say that there are two areas, and those two areas are pi r squared. Wait a second. This looks almost too simple. We see then that we have sigma, or this pi is that pi, this r squared is that r squared, and we see that we have sigma over 2 epsilon naught. And that defines the electric field anywhere above and anywhere below. Notice it doesn't decay, it just is. The electric field everywhere above is, electric field everywhere below is, it just is. And that's only because we're approaching this as an infinitely large plane. That's how we maintain this symmetry. Well, what would it be for the bottom plate? Well, we get the same idea for the bottom plate. I'll call this the top plate. We get the same idea for the bottom plate and we find that to be Q enclosed over epsilon naught A. Doing the same substitution, except now we have a negative sigma. So I have negative sigma pi r squared over epsilon naught 2 pi r squared. Oops, this 2 stays. That pi cancels out with that pi. That r squared cancels out with that r squared. And we're left with negative q over 2 epsilon naught. Okay. The negative helps me understand that these electric field lines are pointing towards this bottom plate. Using the same ideas that we used in just general electrostatics, we need to use some superposition ideas to describe what's going on here. Above, the first thing I ask is above the system. Above the system, the electric field of the top plate is sigma over 2 epsilon naught. The electric field contributed above the top plate because of the bottom plate is downward, which is in the opposite direction, and it is also sigma over 2 epsilon naught. So the negative just tells me that it's pointing towards. So right now I'm going to take absolute value for this problem, and then I'm going to use the idea of away and towards to determine whether or not you need to add. So we have up and we have down. When I take this amount up and I take this amount down, I find that the electric field above the system is equal to 0, because these are the same amount, just in opposite directions. When I look at below the system, I find that we have the bottom plate has an upward contribution, but the top plate has a downward contribution. So when I use superposition, I would say that, yes, again, they have the same amount, just in opposite directions. So when I combine them, I also get 0. So everywhere above the system and everywhere below the system, the electric field is 0. This is a nice question. If you double the charge here, you would do the problem slightly different, but right now, we're just doing it where they have the equal charge. They have the same amount of charge per unit area. And then if I were in between the two plates, I see that this this electric field is pointing down. Well, this one is also pointing down, away from positives towards negatives. So instead of subtracting the two or seeing that they're counteracting one another, they're going together. So I must add the magnitudes of both. So you would do sigma over 2 epsilon naught plus sigma over 2 epsilon naught. And when you do sigma plus sigma over 2 epsilon naught, each one of those, you find that the electric field in between the two plates is sigma over epsilon naught. 1/2 plus 1/2 is 1. And there's an introduction to Gauss's law, thinking about the various types of problems. I will be posting some problems for my students to work on that use these ideas, and then use some advanced ideas that we can talk about next week. I hope that you have a wonderful day. Good luck. Bye-bye.